Is the impulse deleted?
No, impulse is there.
Impulse is okay, ma'am.
Because I think so it's only the basic idea of impulse they have introduced, but already we have completed it. So if it is a subjective based examinations, we will put forward what might be checked as 1 mark, 2 marks, or what concept goes for the 5 marks and 3 marks. Okay, let us start with concurrent forces. What do you mean by a concurrent forces? Suppose if I consider a body, right? Now, there might be n number of forces acting on the body, any number of forces acting on a body. Now, concurrent forces are forces whose lines of action, suppose if I consider, say, force F1, right? Now, the dotted line, which you can see, the dotted line represents the line of action of the force. So it might be force F1, F2, and F3. In this example, there are 3 forces which are acting on a body. Now, you can see that the line of action means look at the dotted lines. Now, all the lines of actions of the forces are meeting at a common point. Which in other words, I can say all the forces are going to act at a common point on an object. Then such forces, we call them as concurrent forces, right? So when, oh, yes.
I'm sorry to interrupt, ma'am. The last thing we did was motion of 2 bodies connected by a string, yeah?
Correct.
Okay.
I'm not very sure because it doesn't appear in the syllabus. Once again, I'll check. So whatever we have done, let it be. Even if it is cancelled, let it be as it is. If it is cancelled as per the CBSE syllabus, then you will not be checked. We have done those concepts, but your examination will not be, will not check those concepts for the examination, right? Okay, boys. So concurrent forces are forces, right, whose lines of action all pass to a common point, or in other words, I can say the forces, all the forces are going to act at a given point on an object, and such forces we call them as concurrent forces. Can you write the statement, boys? Concurrent forces. Concurrent forces are those forces whose lines of action pass through a common point. Suppose if I have this forces F1, F2, and F3. Now all these are going to meet at a common point O. Calculate, sorry, please copy it down. Concurrent forces are forces whose lines of action all pass through a common point. Only one definition is enough right now.
Now, do we have to draw the diagram?
Yeah, draw the diagram. So just label it the forces F1, F2, and F3, and the common point O.
Ma'am, can you repeat the part where you said that the dotted lines denote what?
That the dotted line denotes the line of action. So that is the line along which the force is acting.
Ma'am, so like usually the net force will be 0, right? If it's all coming.
Correct. Yes, the net force should be equal to 0. Yes, F1 plus F2 plus F3 must be equal to 0. Let me put the vector sign because the net force should be equal to 0. Mathematically, this is how we represent. F1 plus F2 plus F3 must be equal to 0. Okay, so this is what we call it as concurrent forces. Now, what happens when concurrent forces are acting on a body which was initially at rest, whether the concurrent forces is going to change the state of a body, whether it is going to change the state of body from rest to motion or from motion to rest. So we'll see what will happen when concurrent forces are going to act on a body. Shall I go for the next slide, boys?
Ma'am, why is the sum 0?
Which one?
Ma'am,
Wait.
why is F1 plus
Okay,
F2
okay.
plus
I'll give you an example. One second. Suppose if I have two bodies, two forces
Ma'am,
acting. Yes, yes, tell me.
ma'am, can you show the previous slide for me? I'll just take the screenshot. Yes, ma'am.
Now, suppose if I have two forces acting on a body, right? F1 vector, F2 vector, and say F3 vector. Okay, all these forces are acting at a common point. Now, let me take these two forces, F1 and F2. Now, let me find the resultant of F1 and F2. I'm just finding, boys, I'm taking these concurrent forces, F1, F2, and F3. Now, all the forces are acting at a common point O. So now let me find the resultant force. So now F1, F2, let me take the equivalent, or I can say the resultant of F1 and F2. So say F1 and F2, the resultant, say I'll go for us F4. Now this resultant F4 is equal in magnitude but opposite in direction to F3. So then F net becomes equal to F3 plus F4. So that becomes equal to 0. There is an experiment, actually, since your laboratory session has not started, we do have an experiment based on concurrent forces as well as parallelogram law of vector addition, where you are supposed to determine the weight of a body. You are going to determine the weight of a body using two principles. One is concurrent forces and the other one is parallelogram law of vector addition. So there you'll understand why all the forces are going, the net forces acting at a common point is 0. So this is how it goes on, right? Equilibrium of concurrent forces. Now you know what you mean by equilibrium. See, when there is no change in the state of rest or of uniform motion of a body on which the forces act, then the body is said to be in equilibrium. What does it mean? Suppose if a body is at rest, you consider a body was initially at rest, right? Now, let any number of forces act on the body. And if the body still remains to be at rest, then we say all the forces acting on the body are concurrent. Are you getting this concept? Suppose I have a body, say of mass m, right? Its velocity is 0, which means the body is at rest. Now, according to this figure, there are three forces, F1, F2, and F3. Three forces are acting on this body. And if the body still happens to be at rest, right? The body is in equilibrium, still happens to be at rest, then what do you understand by that? You understand that the net force is not altering the state of the body. The body is still at rest. Now all these forces add up together, F1 plus F2 plus F3. The effect of all the forces is 0. The net force is 0. That is why the body is not moving at all, right? So the body still continues to be in the state of rest. Then all these forces together, they call them as concurrent forces. Now suppose, look at the second case. Is that anyone, 11B, anyone is having a doubt in this concept? 11B?
No, ma'am.
Only one. Farhan?
No, ma'am. Not out.
Boys, I'm considering a body, right, of mass m. Initially, it is at rest. That is why V is equal to 0. Now, let me consider three forces, F1, F2, and F3. Now, all these three forces are acting on the body, right? When the forces act on a body, right, the net force is 0, which means the body is still going to remain at rest. If the body is still going to remain at rest, it means all these forces are not going to put any change. The net force happens to be 0. Only when the net force is 0, the body still happens to be at rest. Then we say all these forces which are acting on the body as concurrent forces. So that is why concurrent forces are those forces whose sum comes to be equal to 0. They do not alter the state of either of rest or of uniform motion of a body. Now we'll go for another case. You have a body of mass m which is moving with a constant velocity. Velocity is constant, so acceleration is 0. So now three different forces are going to act on the body. Even when these forces are acting on the body still continues to move with the same speed. I'm considering a body where it is moving with a certain speed. When three different forces are acting on the body, F1, F2, and F3, still the body continues to move with the same speed in the same direction. Then the net force is supposed to be 0. Only when the net force is 0, the body, that is what is your Newton's first law of motion. What does Newton's first law of motion states? A body continues to be in a state of rest or continues to move, right? Uniform motion along a straight line path unless and until
Can
an
they
unbalanced
Experienced by
force.
an external force.
Yeah, unless and until an unbalanced external force, which means here all the forces are balanced. Balanced means the net force happens to be 0. So this is what is the application of your concurrent force. Your concurrent forces are not going to change the state of rest or of uniform motion of a body.
Ma'am,
Hmm.
ma'am,
Yes.
is it like all the forces cancels out each other?
Each other. Yes, they cancel out each other.
Okay, ma'am.
Boys, you want to write or should I move to the other one? You want to write this? Do you want to
Ma'am,
write this? Okay. Should I read out? Draw the diagram. Even if it is rough, it's fine. Just complete your diagram, boys.
I have a question.
Okay.
Well, is like when we are pushing an
Hmm.
object, will friction be considered as a concurrent force?
No. Friction will not be considered because friction is a tangential force.
Okay.
We'll do friction next, right? Friction will not act at any point. Friction will not act at any point inside the body. It will be always between the body and the surface on which the body is moving. It's a tangential.
Yes, ma'am.
Shall I move on to the next one, boys? It's that fine, boys. Shall I move for the next slide?
No, we have to do the
Yes,
whole
ma'am.
thing, yeah?
Yes, ma'am.
Yes, boys.
We have to do the
Ma'am,
whole
I'll
thing.
send the screenshot in the chats.
Oh,
Should we write the whole thing in the slide?
yeah, you can write. Otherwise, I'll put this in the sorry slide, the screenshot. You can do it later.
Yeah, ma'am, fine.
Okay, because I think so. I'll have to start with numerical. There's one more thing that I need to state. Tension. There are two things you should know before we move on with the problem solving. One is what we call it as tension. Now, what do you mean by tension? Suppose if I have a rope or if I have a string, right? One end of the string is attached to the ceiling. The other end of the string, say, let me put a weight. Now, what is going to happen is that, say, a wooden block. Now, the weight of the block will act in the downward direction. Immediately, see, the string is not going to snap. The weight of the body tends to pull the string. Immediately, there will be an opposite force acting along the string, and such forces acting along stretched string or springs or rope, we call them as tension. So, tension is nothing but a force acting along a string when the body is pulled by an inextensible string. So this is what you should understand, boys. So whenever you have a string or a rope or a spring, one end of the string you're fixing it to a ceiling, the other end you're applying a weight, right? You're trying to pull the string. Immediately there will be a force acting along the string in the opposite direction. We call such uh, force as tension. So this you have to be clear. And one more thing you need to be clear is normal reaction. I'll do it later. Now we'll start with solving a numerical based on equilibrium of concurrent forces. Is that clear, boys? And then resolution of vector. These are the two concepts which we are going to apply right now. One is your equilibrium, the condition for equilibrium, and second one is your parallelogram law of vector addition, right? Or resolution of a vector. How do you split a vector? These two concepts. Now, yes.
Ma'am, did we have to write tension?
No need, no need. Tension, you should know. What do you mean by tension? That's it, right? Okay. Now look at the question. The question itself will have two diagrams. That's what you understand. First, you have to understand the question. The question has to be now drawn in terms of a diagram. So look at the first part of the question. A mass of 6 kilogram is suspended by a rope of length 2 meters from a ceiling. Is that clear, boys? It's the first part of the question. A mass of 6 kilogram is suspended by a rope of length 2 meters from a ceiling. Look at the diagram. You have a rope of length 2 meter. Now one end of the rope is fixed to a ceiling. The other end of the rope, you're attaching a mass. The mass of the object is 6 kilogram. So its weight W becomes equal to 6 m into g, that is equal to, because g is told to be taken as 10, so it is 60 Newton. Is that clear? This is the first part of the numerical. Is that clear, boys?
Yes, ma'am.
Okay. Now look at the second part of the numerical. A force of 50 Newton in the horizontal direction. So a force of 50 Newton, which is acting in the horizontal direction, is applied at the midpoint P of the rope. Can you see the diagram? The same diagram. This is the first part of the question. Now look at the second part of the question. A force of 15 Newton. Can you see the force of 15 Newton over here? This force is acting along which direction? The force of 15 Newton is acting along the horizontal direction. Now, where is this force applied? The force is applied at the midpoint P. So you have a force of 15 Newton. This 15 Newton is acting in the horizontal direction. Now, where is this force applied? This force is applied at a midpoint P of the rope as shown in the figure. Is that clear right now?
Yes,
Is
ma'am.
that clear, boys? Diagram is clear for you?
Yes, ma'am.
Now, this is the first part of the question. This is the second part of the question. Now comes the third part of the question, right? So where you're applying a force, you're applying a force at the midpoint P of the wire, and this force is acting along the horizontal direction, a force of 50 Newton. Now look at the question. What is the angle the rope makes with the vertical in equilibrium? In equilibrium means this point P. Can you see the point P? Now, at point P, how many forces are going to act? I'll ask Harish. Harish? Harish is
Yes.
here? Harish, at point P, can you identify at least one force? I'll ask the other two from someone else. At point P, okay, 15 Newton. Okay, 15 Newton. Jatin? Jatin? Jatin?
Yes, ma'am.
At point P, there are three forces acting. I think Harish told 15 Newton. What might be the other one?
Ma'am,
What will be the other force? At point P, look at point P. Point P, at point
downward
P,
force,
downward force. What is the downward force?
60 newtons.
Okay, 60 Newton, fine. Johan? Johan?
Johan is
Johan?
not here.
Okay. What happened?
He has gone for passport registration.
Oh, sorry. Jonathan?
Yes, ma'am.
At point P, three forces are acting. One is 50 Newton, one is 60 Newton, the other one. Look at
Ma'am,
point
the tension T1.
T1. Now, can you identify all the three forces, boys?
Yes,
Can you
ma'am.
identify? Fine. Now the question is, what is the angle the rope makes with the vertical? So now this I'll go for the highlighter. Go for now, this part of the rope, right? This part of the rope, and the can you identify the dotted line? Dotted lines. Can you
Yes,
identify?
ma'am.
Okay, this is the dotted line. So the rope is going to make an angle theta with the vertical. So, right, the dotted line is, there is nothing connected along the dotted line. It's a virtual one. Just you're putting this is the vertical. Nothing but this is the vertical, right? So the rope is going to make, at point P, the rope makes an angle theta with the vertical. So that is the question. You have to find the angle theta with the vertical. Are you all clear with the question? Are you all clear with the question?
Yes, ma'am.
Ma'am, in the diagram, what is T2?
T2 is a tension acting. See, 60 Newton is the weight which is pulling the string down. So along, suppose if I put from point P to point W, if I take these 2 points, from point P to point W, you have a string, the rope of length 1 meter, right? So the force which is acting, the tension which is acting along the string, the tension which is acting along the string from P to W is T2.
Uh, okay, ma'am.
So your string now is divided into two parts. Your string is now divided. Say if I put this point as A, I'll just put this point as A. So from point P to point A, the length of the rope is 1 meter. And the tension acting along the rope, see now your entire rope is now divided into two parts, P to W and P to A. Clear? The entire rope is now divided into two parts. From point P to point A, the tension along the string is T1. From point P to point W, where you suspend the weight, your tension is
T2.
that's
T2.
okay. Draw the diagram, boys. Now we have to solve to find the value of theta.
T2 is pointing downwards.
Which one?
The tension
No,
to
no, boys.
T2.
No, it should be upward.
Okay.
T2 should be upward.
Ma'am,
Yes.
and the tension is same through the string, right? Like from P to W and from the
No,
ceiling to the P.
no. If it would have been same, then they would have marked either as T2 or as T1. It's different. It's different. Okay. So
No,
in
ma'am,
this
I'm
case,
talking about like only from the ceiling to P it is same, and from P to W it's different.
different. But in this
Okay.
case, in the first, if suppose if it is diagram 1, I'm just talking about this diagram here, the tension at every point will be the same. Here, the tension at every point would have been the same. Now, since you
Okay,
have
ma'am.
applied a force, it's different. Sorry.
Ma'am, do we have to find T1 to calculate the?
Yes. Asha, okay, should I give you time for you to calculate or should I start doing it?
Ma'am, you can start.
Okay. No, I'll do, right. Homework, in that case, we'll go for that. Okay. Now we'll take only this part of the string, right? So say from point P to point W. Now look at this. The statement is equilibrium. Equilibrium means what? Equilibrium in that sense, the point P is at rest. I'll go for this previous one. This point P is at rest. It is stationary. Neither the point is moving up nor the point is moving down. It is stable, or I can say this weight is stable. And also it's equilibrium. So suppose if when you apply the weight moves down. If the weight is going to move down, then the point P will keep on shifting its position. So point P will not be in equilibrium. So point P is at equilibrium. Equilibrium means it's not moving at all. In that case, T2 must be equal to 60 Newton. Okay. Now we'll go for the other one. Right. Now comes resolution of vector. Now look at this point P, boys. Look at this point P. Now if this point P has to be in equilibrium, then all the forces which are acting at point P must cancel out each other. So can you identify this T1 in the previous diagram?
Yes,
Okay.
ma'am.
Yes. Okay. Now this T1 is a vector. It is a force. It is a vector. Now this vector has to be resolved into two components. Now, we will see why you want to divide this T1 into two components. That I'll do it a little bit later. So now this T1 is a vector. Now T1 is to be divided into two components. For that, I'll mark this point as A, this point as B. This is 90 degrees. Right. Clear, boys? So now only this triangle, I'll just take this triangle separately. So this is 90 degrees. This angle is theta. This point is A. This point is B. Now my aim is to find what is B to P, because A to P is T1. From A to P, the value is T1. My aim is to find what is B to P, and my aim is to find what is A to B. Is that clear for you all, boys? 11B?
Yes, ma'am.
Yes, ma'am.
So now let me find what is B to P, what is A to B. Now in this right triangle, let me find sine theta. And I'll ask someone. Dheeraj?
Yes, ma'am.
Okay. Just in this triangle, just tell me what is sine theta, Dheeraj. In this right triangle, for this angle theta, which is the opposite side? For this angle, which is your opposite side, sine theta?
AB, ma'am.
Dheeraj? Okay, AB divided by hypotenuse is hypotenuse is AP. Okay,
AP.
fine. AP. So then AB divided by what is the value of AP? Value the measurement of AP is T1, correct?
T1.
Then what is AB now? Can you get AB? AB becomes, I'll cross multiply this. Is it T1 sin theta?
Sin theta. Yeah.
Is that correct?
Yes, ma'am.
Dheeraj, is that fine?
Yes, ma'am. Yes.
So that's what AB is T1 sin theta. That is what I am putting it over there. Is that clear, boys? Yes.
Ma'am, so this is how we find the components.
Yeah, this is how you find the components till you get used to all these things. Then later on you will find
Okay,
it.
ma'am.
Ayan is here. Ayan. 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 Advait. Advait.
Oh, ma'am, Advait took TC.
Oh, sorry. Where is Ayan? Ayan is absent. Okay, fine. Jopal. Jopal. Boys, your internal assessment is very, very important, even in class. Whether your values goes the other way, right? You give a wrong answer, that doesn't matter. But if at all you're not answering, then see, they are asking us to take the regular classes, class interaction. So what will I put? So what marks will I put for you people? If you're not answering, do you understand you are in grade 11? Jopal? Okay, I'll talk to them later. Ayan and Jopal.
Now, what is the question again?
Who is this?
What is Taisir?
Find the value of cos theta. Cos theta will be BP divided by adjacent side divided by AP. Or I can write BP is equal to AP cos theta. So that becomes equal to AP is T1. So BP is equal to T1 cos theta. That's what.
Ayan
Yes.
replied. Ayan replied.
Oh, okay, fine. So BP is T1 cos theta. So all these values I'm translating, all these value I am translating over here. This I marked it as A, and this point I have marked it as B. So now look at this. AB is T1 sin theta, BP is T1 cos theta. Right? Now can you see these two sides? Now those two sides which I have marked, they are parallel to each other. If AB is T1 sin theta, so the parallel line from point P to the left is also T1 sin theta. Is that clear, boys? Is that clear?
Yes, ma'am.
Okay, fine. Now one more question. Now you have split T into two components, T1 sin theta and T1 cos theta. Now it's over. Now look at this. If the point P to be at equilibrium, the point P is at equilibrium. Is that clear? Which means the downward force which is acting at point P must be equal to the upward force acting at point P in the upward direction. So what is that? If point P to be in equilibrium, equilibrium means neither the point is moving upward nor the point is moving downward. Is that clear, boys? Vertically in that sense, point P neither moves vertically upward nor vertically downward. Now, what will be the condition for that? The upward force T1 cos theta must be equal to the downward force 60 Newton.
Yes,
Is
ma'am.
this the equilibrium condition? So start writing this. For point P to be in equilibrium, vertically means what? Neither the point P should move up nor the point P should come down.
Ma'am, I think the period is over.
Oh, sorry. Boys, if it is very difficult, you tell me.